Okay, good evening, everybody. And welcome to another session of organic chemistry. In today's session, we are going to start with the chemistry of alkenes, which is in chapter 7 of your book. No. Don't worry about that yet. Okay, so we are going to start with chapter 7, of course, which is dealing with the chemistry of alkenes. Now, before we get, I will start the session. However, I do want to make a couple of announcements. Our own work assignment for this week will be posted, and today and it will be due on Sunday. That is October 7th at 11 p.m. And then on Wednesday, tomorrow, that is October the 3rd at 8 p.m., we are going to have an online review session based on Chapter 7, end of Chapter 7 questions. That is tomorrow at 8 p.m. I will send you a reminder tomorrow and send you the link for that session tomorrow. We are essentially going to use the same link that we have been using for the rest of the semester. But just for the benefit of those who may not have the link, I will send the link again tomorrow. Okay. Yeah, Lenisha, can you read for us what topics we are going to cover today? Can you read for us what topics we are going to cover today? Yes.
Okay, today's topic is concept nomenclature of alkenes, degree of unsaturation, relative stability of alkenes, electrophilic addition reaction. Okay,
those are all the topics we are going to cover today. The rest of the topic we will cover on Thursday. Okay, so just as Glenisha has read for us, we are going to start the discussion of the chemistry of alkenes. However, before we do that, I also want to call your attention to this slide in front of you, which is essentially the learning outcome objectives. These are some of the more important concepts and topics that you should be able to perform at the conclusion of this chapter. So I will urge you to continually come back to this page to see whether you have actually mastered all of these concepts here. So at this point, the question is, what is an alkene? Alkenes are those organic compounds that contain the carbon-carbon double bond. Yeah, do you have a question? Alkenes are those compounds that contain the carbon-carbon double bond. The carbon-carbon sometimes they contain only one carbon-carbon double bond. Sometimes they may contain several carbon-carbon double bonds. For example, you have this molecule here. This is the smallest alkene, in which you only have 2 carbon atoms, and you also have a carbon-carbon double bond. in which in the carbon-carbon double bond you have a pi bond, and then you also have a sigma bond. And all of the carbon-hydrogen bonds are sigma bonds. Sigma, 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 and then one sigma between the two carbon atoms, and then the pi bond between the carbon atoms also. Now, if I want to give you the orbital picture of this structure here, simply writing the sigma bond as line bonds, you will have a p orbital on each one of the carbon atoms, so you have a p orbital on each one of the carbon atoms, and in each of the p orbital you have an electron. So in order to satisfy the tetravalency of carbon atom, the electrons in the two p orbitals will overlap. That will be an overlap of the p orbitals. So we could represent the overlap as this. In which essentially we now have those. Sorry about that. We now have the electron. It is back. Those two electrons will now be between think of those two electrons between the overlap, the two p orbitals overlap, and those two electrons are within that overlap region. And so therefore, if for example I want to write a resonance contribution for this molecule here, supposing I move these two pairs of electrons, this pair of electrons, draw this arrow, I move the pair of electrons to this p orbital here. Now we could have a resonance structure in which now we have that pair of electrons is now residing on only one of the p orbitals. And what do you think the formal charge on this carbon will be? What will be the formal charge on this carbon here? So therefore, the formal charge will be -1, right? And will there be a charge on this carbon here? Keep in mind we have moved this electron away. Positive charge. Okay. So that is the basis for writing resonance. Whenever you have a pi bond between two atoms, in essence, the electron in the pi bond is being shared by two p orbitals. So by writing resonance, all we are doing is moving those two electrons to one of the p orbitals. And that is why we always tell you resonance only involves sp2 hybridized atoms or sp hybridized atoms. at no time do you write a resonance that involves an sp3 hybridized atom, because there is no available p orbital. Okay? So therefore, if we say this is structure A and this is structure B, structures A and B will be resonance structures. So you see the basis for us writing resonance structure. For example, what we normally do, if I have this, I move this to here. Okay, so that is the basis for this type of resonance structures. Because we are simply, at this point, we are assuming that this electron here, this pair of electrons is in a p orbital, and the p orbital here is vacant. Now I bring this up because most of the chemistry of the alkenes will be focusing on the carbon-carbon double bond. It will also be focusing on the fact that the bond, the pi bond, is not as strong as the sigma bond. So we are able to perform a lot of chemistry using the pi electron. So as we move along during the course of this chapter, you will see some of that. So all of the physical properties and the chemical properties of alkenes is actually derived from the fact that we do have that carbon-carbon double bond. So the carbon-carbon double bond is what we refer to as the functional group. For alkenes. Okay, so at this point, let us start with the nomenclature of alkenes. We know alkenes are carbon that contains compounds that contain carbon-carbon double bond. So let us say alkenes and IUPAC nomenclature told you the simplest alkene is this here. The name of the IUPAC name for all alkenes are derived from the corresponding name of the corresponding alkane. For example, we call this ethene. And how do we derive that? It comes from ethane. And to derive the alkene name, what you do, you remove the A and E ending of the corresponding alkane, and you replace with E and E. So therefore, if I have this, what would be the name of this alkene? Anybody? Propene. Very good. This is propene. That would be the IUPAC name. How about this one here? What would be the IUPAC name for this? Butene. Would that be sufficient to describe that molecule? Okay, let us try this. We'll come back to that. Supposing I have this. What will you call that? We we call that butene too? Why not? Is this a butene? Right? Okay. So the point here is, to name the alkene, what you have to do, you have to use number to indicate the position of the double bond. In this case, you have to number the longest carbon chain that contains the carbon-carbon double bond. Keep that in mind. You got to number the longest carbon chain containing the carbon-carbon double bond. So in this case, this is carbon number 1, and you have to number this so that the carbon-carbon double bond will be given the lowest possible number. So that is carbon 1, 2, 3, and 4. So therefore, what will be the name of this alkene? 1-butene. So it's a 1-butene. And this one becomes, this is carbon 1, 2, 3, and 4. Okay? There is a double bond between carbon 2 and 3, so you use the lower number to indicate the position of the carbon-carbon double bond. So this becomes 2-butene. Now supposing I give you this. What would be the name of this alkene? Okay, the first question is, what is the longest carbon chain? The longest carbon chain? Is it 6? Where do you start counting? Okay, I'm not saying you are right. Let us see whether that is correct. Okay, we start counting from here. 1, 2, 3, right? Where do we go? But keep in mind, we have to include the carbon-carbon double bond. Okay, so therefore, that will not work. Okay, start from here. Okay, good. Okay, good, good. Very good. Very good. So keep in mind, when you look for the longest carbon chain, you have to include the carbon-carbon double bond. So in this case, the longest carbon chain starts from here. Also, keep in mind, you got to give the number so that the carbon-carbon double bond is assigned the lowest possible number. So this is 1, this is 2, this is 3, 4, and 5. So the longest carbon chain is 5. So the base name will be what? Pentene. Very good. The base name is pentene. And therefore, what do we have a branch in position number 2, right? You have an ethyl group in position number 2. So what do we call this? Okay, very good. So you find, because you guys are already familiar with the nomenclature of alkane, the nomenclature of alkane will be fairly simple. So this becomes 2 ethyl, one pentene. 2 ethyl, 1 pentene. Now, when you are the cyclic alkene, with the cyclic alkene, if you have, for example, you have this here, you do not need to indicate the position of the double bond if you do not have any branches. Okay, in this case, this becomes what? This becomes cyclohexene. Okay, very good. You do not need to indicate the position of the double bond. However, supposing you have this. Yes. No. Cyclic, that's a different story. Just being a cyclic molecule doesn't mean it is aromatic. Most aromatic compounds generally contain cyclic rings. So it doesn't mean that if it is cyclic, it's aromatic. So anyway, we're going to get to that sometime in the future. Okay. So anyway, so supposing we have this. Supposing we have that. Okay. How are we going to name this? Well, I'll give you a hint. We are going to name this as a cytopentene. Okay? Cytopentene. So how do you think we are going to number this? Okay, is it 1,2 dimethyl? Keep in mind the focus is on the carbon-carbon double bonds. Okay, so where's the position number 1? No. In this case, if you have an alkyl group on the carbon-carbon double bond, okay, that carbon that has the alkyl group takes position number 1. Okay, in this case, this is position number 1 and position number 2. Okay, if you have a carbon-carbon double bond, okay, and each one of them, of course, could be position 1 or 2. If you have an alkyl group attached to any of the carbons, the carbon that has the alkyl group becomes carbon number 1. Okay, okay, which is what we have there. Okay. So this is position 1, 2, 3, 4, 5. So therefore, what do we call this compound? What is the name? 1,5 exactly. So this is called 1,5 dimethyl, okay, cyclopentene. Okay? Okay, cyclopentene. Okay? Because at this point, you do not need to indicate the position of the double bond when you have the ring system. It is assumed in the ring system, the double bond will always be position 1 and 2. Okay. Okay. Now, supposing I have this. What will be the name of this? What will be the name? The longest carbon chain? 5, okay? So we're going to start numbering from where? It doesn't really matter at this point, right? Okay. So you say 1, 2, 3, 4, 5, and 6. You see that? Which one? We go from here to here, the longest carbon chain containing the double bond. No. That's in the cyclic molecule. That's in the cyclic molecule. But in the long chain molecule, you have to assign the lowest possible number to the carbon-carbon double bond. In the cycloalkenes, the double bond will always be position 1 and 2 in the cycloalkenes. In other words, this here. The double bond will always be position 1 and 2. But in the long chain, the position of the double bond will have to be the lowest possible number. Okay, so now, so what will be the name of this here? Is that enough for this about the stereochemistry? About the stereochemistry. You have these two methyl groups on one side of the double bond, right? And then you have the ethyl group on the other side of the double bond, on the same side of the double bond. Exactly. So what do we call that? Cis, exactly. So now we call this cis. Cis. Okay. 3,4 dimethyl. Okay, cis 3,4 dimethyl. 3 what? 3 exactly. 3 hexene, right? Okay, you see that? Now, supposing I ask you to write the trans 3,4 dimethyl 3 hexene, what would it look like? Supposing I ask you to write the structure for trans 3,4 dimethyl 3 hexene, what would that look like? Trans, yes. Okay. So we do we flip them, right? Very good, very good. So now this becomes, we write this here. So we could now say this methyl could be here, and this other methyl could be here, right? And then this is here, and then this is here. And so this becomes trans 3,4, right? 3,4 dimethyl 3 hexene. Now this, let us call this, to make things easy for ourselves, molecule A and molecule B. What will be the stereochemical relationship between these two, A and B? Would this be configurational diastereomers? Do you have chirality centers in there? Don't forget the configurational diastereomers, you must have chirality centers. That is why we call them configurational diastereomers. So these here we call cis-trans diastereomers. These are called cis-trans diastereomers or geometric diastereomers. We call this cis-trans or we call them geometric diastereomers. Because they are diastereomers, in other words, these diastereomers are stereoisomers that are not mirror images. And because they are direct stereomers and they do not have chirality centers, the reason why they are direct stereomers is because of the fact that we have cis-trans isomers because of the geometry. Okay? The restriction between the carbon-carbon bonds. You cannot move them. And that is why we call it geometric direct stereomers. Okay. Now supposing I give you this molecule here. Supposing I give you that, what are you going to call this? What are you going to call this? Propene, okay, fine. Okay, by the stereochemistry. Will you call it cis or trans? Because how do you do that? That's a problem, isn't it? Okay? Because that is a problem, therefore, when we also now have an alternative nomenclature for alkenes in which we use the can-ingo prelog system. I'm sure you've heard that before. Okay, what we call the easy system. Easy system or ZE system, if you want to put it that way. And how does that work? Exactly. Okay, you guys already know that. Now, what do we do? What do we do? We now say, okay, just as in the case of the chirality centers, we focus on one carbon at a time. Okay? So let us focus on this carbon, and then we assign priority to the atoms attached to this carbon based on atomic number. So what is priority A? Focusing on this carbon. This is A, therefore this is B. Okay, we finish that. Then we come to this carbon. Okay, now we focus on this carbon. What is priority? Chlorine A and B, right? Now, whenever you have, okay, let me write this. Whenever you have groups or atoms of same priority on the same side, groups or atoms of same priority on same side, we call this Z, the Z isomer. We say Z stereochemistry. Whenever they are on the opposite side, opposite side of the carbon-carbon double bond, opposite side of the carbon-carbon double bond, then we call this the E isomer. Okay? So therefore, how do we name this one here? Okay, we have the priority A on this side, priority A on this, so that would be the Z isomer. So therefore, to name this molecule, we say Z, put in parentheses. Okay, by the way, we need to say, okay, well, we just leave this as it is for now. Z, and then you give the name as you normally give it. What will be the parent chain? Propene, and so you put carbon number 1, right? 1, 2, and 3. So this becomes 1 bromo, 2 chloro, right? 1 fluoro in alphabetical order. Propane. It's redundant at this point. Propane. I know what you're saying. But at this point, we don't need to put 1 on propane because it doesn't really matter. You know, you could only, propane. If you say propane, it can only be on 1 anyway. You follow that? Okay. If you put it, I will not, penalize you, but you don't really need to put it here. Okay, now, let us look at another example, yes. Okay, so this becomes Z, 1 bromo, 2 chloro, 1 fluoropropane. Supposing I have this. Okay, how are we going to name this using the Kahn-Ingold or the easy system of nomenclature? What is the longest carbon chain? 5. Where do you start the number? Okay, this is carbon 1, 2, 3, 4, and 5, right? Okay, good. So now how do we name this? Okay, let us do priority. This is A, focusing on this carbon here. This is A, and this is B, right? About on this carbon here. This is A, and this is B. Okay, so what would this be? E, exactly. So this becomes E. Okay, but what E? We got to indicate the position of the E, the stereochemistry at this point. This is 2E. Now you say 2E because the double bond is in the 2 positions. So you say 2E, paren. What? Oh, is it? Yes. Yeah, in this, if you just say E here, you'll be fine. But the reason I'm saying that you need to put 2, you're going to see that later. Because supposing you have more than 1 double bond, okay, you have to indicate the position of the double bond and then the stereochemistry. So in this particular instance, you only have 1 double bond, so you will get away with 1, just E, without using the 2. That's fine. Okay, so you could say 2E, 2 bromo, okay, 2 bromo, okay, 2 bromo what? 2 pentene, right? Okay. Yes. Huh? Why is 2E? Okay. What I was saying is, you don't have to put these 2 here. Okay. You don't have to put these 2 here because in this particular instance there is only 1 double bond in this molecule. But very often you may have more than 1 double bond, and therefore you have to indicate the position of the E. What is the E? Okay, that is why I'm putting 2E here. But in this particular instance, you don't have to put the 2. Yes.
On the last one, the one before that one,
This one here?
oh, just okay.
Because it doesn't really matter. That you only have one choice here. Okay. Okay. Now let us give. Okay. Now, supposing you have this. Supposing you have this. Okay. Let us now give you a little bit more complexity. Supposing you have this molecule here. I'm sure you guys can do this now. You can do this, right? Can you name this molecule here? Let us try this. Yes. Why is it E? Because it is E. I'm sorry. This one here. The one I said was 2E? Oh, okay. This one here? Why this one E? Because the group of same priority, this group here, priority A and priority A here, they are on opposite side of the double bond. When they are on opposite side of the double bond, that is trans. When they are on the same side of the double bond, that is cis. When it is on opposite side, we say it is E. That is the convention. When the group of same priority and are on opposite side of the double bond, the convention says that it must be E. Okay. And when they are on the same side of the double bond, the convention says that it must be Z. Okay. Okay. Yes. Because the double bond is in the two positions of pentane. This is carbon number 1, 2, 3, 4, 5. Huh? The double bond is in the two positions right here. Okay. Okay, now let us go back to this. Okay, can you name this? Okay, what is the longest carbon chain? Where do you want to start numbering? 1, 2, 3, 4, 5, 6, 7, and 8. That is octane, right? Very good. And the branches are where? Let us see the branch. You have a branch in 7 position. You also have another branch in 4 position. Any other branch? In 3 position. Very good. So this will become, and in terms of the easy nomenclature, what will it be, Z or E? What is it? Okay, let's do the priority. This is on this carbon here. This is A, and this is B. On this carbon here, this is A, and this is B. So that would be Z. Okay, so that is Z. Okay, I want to satisfy you guys, so I am not going to put a number on it, since we only have one double bond here. So I'll put in paren Z, right? Okay. Okay, what is the rest of the name? Alphabetical order. For ethyl, don't forget, you see, I have to follow all of those rules that we used in with the alkanes. For ethyl, for ethyl, 3, 7, very good. 3, 7. Let me take this out of the way. Three, 7. Dimethyl, right? Two octane. Very good. Okay, I think you guys are getting the idea. What? Wait, no, I said I wanted to satisfy you guys since you, okay, you don't have to. Remember I said you don't have to if you only have one double bond. Okay, so in this case we know that the Z is relating to the only double bond you have in the molecule. Okay, now how will you name this? This one here. Here you have two double bonds. What is the longest carbon chain? What's the longest carbon chain? We have that. Okay. 1, 2, 3, 4. Oh, I'm sorry. 4, 5, 6, 7, and 8. It's an octane, right? Okay, very good. Now, since we now have two double bonds, we got to assign stereochemistry to each one of the double bonds. When we say stereochemistry, whether it is Z or E. Okay? Now, to do that, you focus on one carbon-carbon double bond at a time. Keep in mind, focus on one carbon-carbon double bond at a time. Okay? And where are the branches here? The branches are 5 and 4. At 5 and 4, right? 4 and 5. Okay, very good. Okay, so what do we do to name this? So what I will do, I will focus on this carbon-carbon double bond, right? Okay, based on this carbon here, what is A? So this is A, right? Okay, this is B. And based on this carbon here, let's focus on one carbon-carbon double bond at a time. Based on this carbon here, what is A? This is A, and therefore this is B. So what is the stereochemistry? Therefore, we have to say now indicate the position of the double bond. It is 2Z. So now this is 2Z. 2Z because you have the two groups of the same priority are on the same side. I see you guys having fun over there. Okay. So they are on the same side, so that is 2Z, right? So now, we now come back to this other double bond, right? Let's take all this out, right? We now focus on this here, this double bond. So, on this carbon here, what is A? The top one, right? Good. This is A. And this here is therefore B. On this carbon here, bottom, A. And this therefore B. Okay. So, what is the stereochemistry? E, because the groups of similar priority are on opposite side of the double bond. So therefore, this is 4E. Keep in mind, we say this because the first carbon-carbon double bond is in position number 4. So we therefore call this 4E. Okay, so what will be the name of this compound? Let us now give the complete name of this compound. 2Z, very good. In paren, this is now where the number is most important. Now you have to indicate the number. Okay? Now it becomes 2Z, 4E, paren, 4, 5, okay? 4, 5, dimethyl 2,4-octane. You also need to indicate the position of the double bond. So become 2,4-octane. You follow that? So now I could give you this name and say, give me the structure. We could go the other way. This metal here, right? This here. That's part of the chain. That's part of the chain. Yes. Huh? Well, I told you because there are certain instances where we cannot do cis and trans. We cannot use cis and trans. I gave you an example of okay, I remember I gave you this example here. I said, supposing we have this. The question is, why do we need this easy system, right? As I told you, supposing we have this. Okay, how are you going to use cis and trans to name this? There is no basic. What are you going to say is cis? What are you going to say is trans? Relative to what? So, because of situations like this, okay, therefore, we have the alternative way of naming alkene as indicating the stereochemistry, okay? And that is the easy system. Okay, so I'm assuming at this point that you guys have gotten the idea. Okay, so let us go back. Okay, okay, we'll do that. Let us do that. Okay, so we finished this, right? Okay, this is the one we just did. Okay, we did this already. Okay, if you look at this, this is our octane, 3,7-dimethyl, 4-ethyl, so we did that already. Okay, this will be the E isomer. Okay, lower priority, this is B, of course this is A, this is B, and this will be A. You see why it is E isomer. Okay, we did this already. 2Z, 4E, that's what we just did. And this will be your B priority. This is A. This is B here. This is A. And on this here, this is B, B, and A. Okay. Oh yeah, you have to. Yes, yes, yes. Very good. Now, so thank you for bringing that up. Okay, let me go back. I'm glad you brought that up. Okay, I made a slight mistake here. Whenever you have more than one double bond, yeah, thank you for bringing that to my attention. Whenever you have more than one double bond, in this case, you have, in this particular instance, instead of calling this 2,4-octane, because you have two double bonds, you have to indicate that you do have two double bonds. And to do that, you remove the A and E ending, of the corresponding alkane. You remove the NE ending, and you replace with whatever. In this case, you have di. You have two alkenes, so it becomes di, and then the word in. Okay, so that becomes a prefix, so that becomes di. So in this particular instance, sorry about this, let me change this. Instead of saying octane, this will become octadiene. Octadiene. Okay? In other words, remove the NE ending of the corresponding alkane and you replace with the prefix di in this case because you have two carbon-carbon double bonds, and then the word in at the end, di-in. Okay. 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 Now, if you have three double bonds, it becomes octatriene. If you have four, it becomes tetraene. Okay, so we are going to see some examples of that. Oh, I'm glad you brought that to my attention. Okay. Now, let us name this. Let us name this. Okay, well, the name is already here, but how do we justify this? The name is here, okay? The name is here. Let us number this. Where do you start the number? Okay, very good. So we start to number from here in order to give all of the carbon-carbon double bond the lowest combination of numbers. So this is carbon number 1, 2, just a minute, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the branches are in position 11. You have branches in position 11, that's a methyl, right? In position 7, a methyl. In position 3, another methyl. Okay. And the double bonds are in position 1, 3, that's what you have here, see this? 6, and 10. And of course you have tetraene at the end. Okay. Now, how do we get 3E and 6E? Now the question is, why don't we have stereochemistry for the 1E and the 10E? How come we did not indicate the stereochemistry for those double bonds? The answer is, anytime you have a carbon-carbon double bond in which any one of the carbon is attached to the same atom or groups, then you cannot have stereochemistry. You cannot use Z or E stereochemistry. So there is no base. Okay, write it down. Okay. Okay, let me write it down. Okay. Okay, in this case, let me show you here. I'll write it down. Okay. In this case, what you have here, on this carbon here, we have hydrogen here. We also have hydrogen here. Okay? On this carbon here, you have a methyl here. You also have a methyl here. So, let me write this down. Anytime anytime a carbon of the carbon-carbon double bond is attached to the same two groups, or the same two atoms, the same two atoms or groups, then you cannot have, then you cannot have easy stereochemistry. Z stereochemistry. Is that clear? And that is why, if you take a look at this, this carbon here is attached to 2 hydrogen atoms, so there is no basis for us to assign priority here. The same thing here, this carbon here is attached to 2 methyl groups. Let me take this out so that we know that. You can see this is a methyl right here. And this is another methyl. So there is no basis for us to assign priority. So in that case, you cannot do easy stereochemistry. And you notice here, the only easy stereochemistry we have here is in the 3 position, we say 3E, and in the 6 position, we also say 6E. I believe one of you asked, how did we get 3E and 6E? Did somebody ask that question?
Yeah.
Okay. You want us to do it?
Yes, please.
Okay. Okay, so let me take all this out. Okay, the stereochemistry of interest. Keep in mind right here, this is the 3 position, right? Keep in mind right here you have hydrogen. Okay. Also keep in mind right here, this is the 3, 4, 5, 6. This is 6 carbon. Also keep in mind there's hydrogen here. Keep in mind you also, anytime you look at the carbon and it doesn't have all of its bonds, then you know that the missing bond will be hydrogen. Okay, so how do we arrive at 3E? Let us look at this here. Okay, they focus on this carbon-carbon double bond. Let us look at this carbon first, which is priority A. On this carbon, focus on this carbon here. The methyl, right? This is, oh no, I'm sorry. What is A? This group is A, and this is B. Then we come to this carbon here. Where is the priority? A, this here? A, and this is B. Okay, what is the relationship between the, okay, so that's how we got E, 3E. So we come to here. So this is 3E. I'm sorry. 3E. Now we come to here. Let us assign the priority here. Take this out of the way. Okay, we focus on this carbon. What is A? Below A. B is there for hydrogen. Then we focus on this carbon. What is A? And therefore this is B. Okay? So therefore this is what? E. And that's how we got 6E. 6 because the double bond starts from the carbon number 6, which is this here. Okay? So everybody follow this? So at this point you should be able to do alkene nomenclature using the easy system. What time do we have? 7:15. We've got plenty of time. Now at this point now at this point we want to change gear. We got plenty of time. At this point we want to change gear. Okay. Remember, I'll come to this. I'll come back to this. That's 15. Now, supposing I give you this molecule here, I give you this formula here, C6, H10, and I tell you to let me know how many double bonds or rings are present in this molecule? Yeah, how many double bonds? Or rings? Or even triple bonds? Are present in this molecule? Okay? To answer that question, you could use this formula here. What we call the index of hydrogen deficiency. You need to know this. You need to memorize this formula here, because we are going to be using this formula all through organic chemistry. Okay, this is the formula right here. Index of hydrogen deficiency. And that essentially means, some people refer to this as degree of unsaturation. But I prefer to use index of hydrogen deficiency, because this also applies to cyclic molecules. And very often we do not consider cyclic molecules unsaturated unless they have carbon-carbon double bond. Okay, so index of hydrogen deficiency, IHD, what that is, it gives you the number of carbons. The C stands for the number of carbons in the molecule, minus the number of hydrogen in the molecule divided by 2, minus the number of halogen in the molecule divided by 2. X stands for halogen. Halogen is bromine, chlorine, or iodine, divided by 2, plus the number of nitrogen in the molecule divided by 2. The C, the number of carbon atoms, plus 1. Okay, so C stands for carbon. So let us use this formula here. For every index of hydrogen deficiency, for each index of hydrogen deficiency, that means you have one double bond, or one ring, okay, just a minute. Okay, for each index of hydrogen deficiency, that means one double bond, or ring. Supposing you have two index of hydrogen deficiency, equals to what? What does that mean? Two double bonds, or two rings, or what? Or one double bond and a ring, or triple bond, Triple bond is a carbon-carbon triple bond. Okay? So that is what the index of hydrogen deficiency gives you. Okay, so therefore, let us go to that problem I gave you. Yeah, it doesn't tell you specifically, but it gives you enough information, and then down the road, we will give you additional information that will allow you to determine the structure. Huh? Yes. Okay, so let us see here. I told you, supposing I have this here, C6H10, okay, what would be the index of hydrogen deficiency? Let us use the formula. IHD equals to number of carbon minus hydrogen divided by 2 minus halogen divided by 2 plus nitrogen divided by 2 plus 1. Okay? So based on this formula here, what is C? 6 minus 5. We don't have hydrogen, we don't have halogen, so we don't need to worry. So that is nothing. And we don't have nitrogen, so we don't need to worry. So plus 1. So this is what? What is it? 2 double bond. Okay, 2 double bond, okay. 2 IAD, okay. So what does this mean? So therefore, if I tell you a molecule has an IAD of 2, and I give you this formula here, and I say, give me a possible structure, what will you give me? Okay, let us see. That's fine. You could give me anything, right? Okay, so you want to give me this here, right? How many more carbon do we need? Okay, does that fit? Does that fit the formula? That's fine. Okay, but can you also give me something else? A double bond and a ring, right? Okay. You can also give me this, right? And what? What is missing? A double bond, exactly. Okay. What is the relationship between this molecule and this molecule? Are they isomers? Yes, they are isomers. What kind of isomers are they? They are what type of isomers? What type of isomers? Constitutional isomers, yes. They are constitutional isomers. Okay. Now, okay, so let us finish this here. Almost. We are almost done. Almost done. Okay, so this is just using this formula here to determine the IAD for using this formula, and that is 4. Okay, you have an IAD of 4. So what does that tell you about this molecule? If you have 4 double bonds or a combination of ring or double bonds, so that's left to you. But I will give you additional information. Yes. Okay. Okay, about this one here. Let's do this. Let's do this and we go home. No, let's do this and we go home. Okay, but this is easy. This is easy. So supposing I ask you to give me the index of hydrogen deficiency of this molecule. How many? No. You don't have to. Just you don't need. You already have the molecule. Okay. What is the index of hydrogen deficiency here? Exactly. So what is it here? Let us count it. The one ring is 1, right? Double bond, that's 2. That's 3, 4, 5, 6, 7, 8, 9, 10, 11, right? 12, and then the ring 13 is okay. But the reverse is I could give you the formula for this molecule, and I could give you the formula, right? And say determine the IAD. I could do that also. Why not? Why not? So anyway, at this point, we have come to the end of today's presentation. I will see you tomorrow at 8 p.m. There will be a quiz on Thursday. There will be a quiz on Thursday.